from the University of Southern Queensland and the National Centre for Engineering and Agriculture. Would you please give an enormous welcome to Associate Professor Bernadette McCabe.
Thank you very much for that introduction, Chris, and I welcome you all this morning to have a listen about bioenergy for the next hour or so. Just to continue some personal stories, I was actually from University of Sydney. I commenced my undergraduate, now this is showing my age, 30 years ago as of next year. And I did a Bachelor of Science in Honours and did an honours degree in microbial ecology, so I spent a lot of time over beyond Wentworth Building. I did a lot around Carslaw Building, and so coming back on the campus is a really nice personal experience for me too. And I can relate to Chris's story about growing up at universities and doing spending time and holidays, not from my point of view, but from my son's point of view. I don't know if you remember, but there was a little kid walking around last week. He's my son, Hugh, who came down to visit his grandma, and my mother's still in Sydney, and I thought what a better way to expose him to the wonders of science than to mix in with the big kids. And you know what, he had a fascinating day. He loved it. Not that he understood anything about fusion in that lecture, but he just absorbed it like a sponge. And I think that it's never too young to encourage and foster a love of science. And that's one of the things that I love to do as a scientist, is to go into the schools. And it includes teaching bigger kids like yourselves, those that are probably going to turn into some really great scientists of the future. So to just go on to today's topic and elaborate a bit more on the importance of bioenergy, as Chris mentioned, I'd like to spend the time to discuss and talk a bit about this, how it can be a sustainable, reliable and multifunctional energy system in the same way that Chris was mentioning. So an overview for the presentation is to firstly look at what feedstocks are available for bioenergy and the different conversion technologies, because there's a multitude there, and that it's integral to match both feedstocks and conversion appropriately. I'll then go on to discuss the end utilisation of that energy, because again, being a very flexible system, it can either be used in the form of bioelectricity, can also be used as a fuel, and also heat. So out of all of the renewables, it is the most flexible in that regard. I'd then like to talk a bit about biogas and what a closed-loop system means. Biogas is actually my area of expertise. So to discuss bioenergy in its broadest sense really makes no sense for me, because I could be really overstepping the mark in terms of where my expertise area lies. So I want to spend a little bit of the lecture on actual biogas production. And then finally ending on the sustainability of bioenergy into the future. There's been a lot of public debate in terms of its sustainability, the food versus fuel debates that have been going on in the US. And so we want to be able to dispel some of those myths that are out there and just to understand where it's placed, where bioenergy is placed, will be in terms of renewable energy into the future, given our theme for this science school is future power. So let's have a look at feedstocks. As I said, there's a multitude of feedstocks, and as we progress into the future, there will be more novel feedstocks to come. So we can broadly divide it into energy crops or the utilisation of waste. Now, because of the debates that are going on with energy crops, we are seeing more utilisation of waste, and that really makes sense given how much we are producing with increasing population and so on. So to talk a bit about energy crops, they're based on what the component is in terms of how we can extract the energy. So we can talk about oilseed crops, right? So they will be predominantly used in, say, the transesterification processes, so we can produce biodiesel, so that's the end product there, that's the fuel. In terms of grains, We can talk about things like maize, sorghum, all of those. And again, those feedstocks will be used in a different conversion technology to produce a different end product. Sugar crops, things like sugarcane. Use a lot of that in Brazil to produce biogas and also to produce ethanol. So 2 different conversion technologies to produce 2 different products. And we can also use trees and grasses. Grasses is particularly useful in areas like Ireland, which are using grasses in their production of biogas. There's been looking, I think, even in Australia, across the supply chain for mallee. So trees could be a good way of using, woody crops as a biomass for energy. Now, that second category, as I referred to as being a little bit more, getting more traction and importance, is that of waste. So we can use agricultural residues. Agricultural residues, things like trash from cotton gins and also other straws and the like. All is very cellulosic or lignocellulosic, so not going to be really suitable for biogas production, but could be for fermentation into ethanol. Food waste is becoming quite big, which I'll talk about a little bit later as well. Now, because food waste has a lot more water content, it's not going to be great for combustion, and so it's got to have a technology that will suit, and that one's more around anaerobic digestion. Sludge from wastewater treatment. Again, this waste is important in the production of biogas, as is wastewater from food processing like abattoirs, which I will talk about more later as well. So those conversion technologies that I started to mention are based on 3 different processes. They can be a thermal process, which would include just simple burning or combustion. It can be gasification, which is at a higher temperature, or even pyrolysis, which is high temperature in the absence of oxygen. Now, these thermal processings will produce heat and power, or even chemical feedstocks in the case of pyrolysis. Chemical feedstock like biochar, you might know, which is important in terms of soil conditioners. The other type of conversion, is the biochemical. So as the name says, it is based on the conversion using microbes. And so we include things like anaerobic digestion. I'll just talk about anaerobic digestion, and also fermentation. Now, 2 different processes, which I will talk about in more detail later on, again, looking at the metabolic pathways. And the third conversion technology is that of a chemical, and that is principally around the transesterification process to produce biodiesel. So you remember in that other previous slide, when I said a feedstock like oil crops, that's important to what you do is they have the fatty acids, so of course the glycerol backbone with the 3 fatty acids coming off them. The ester linkage is then transesterified so that we have the fatty acids available, and that's the production of biodiesel. Okay? So to put it together, hopefully you can see this up the back. This is a neat little diagram which basically matches the substrate or the feedstock with the right technology, and it goes on to show the products that are produced. So if we go back to the type of biomass or feedstock, it's the 2 interchangeable terms. I mentioned the oilseed crops. The part of the plant that's used, or that component, is the fats and oils. And then through that chemical process, which I mentioned about transesterification, or there's another one that's called hydrocheating, we will end up with the product biodiesel or renewable diesel. Grains, as I mentioned, like sorghum and maize, the component macromolecules, starches are extracted, and then we can undergo a variety of biological changes, including some conventional alcoholic fermentation, and that will produce your ethanol or even butanol. Then if the sugar crops, we mentioned sugarcane, the extracted is the monomer sugars, again undergoing conventional fermentation to produce ethanol. Now if we go down to the more of the ag residues, and it's a part of the waste, and it also includes other things like wastewater treatment plants and the sludge, it will have cellulose, hemicellulose, lignin. The diagram I don't quite like here, but it also includes fats and oils and also other proteins. But basically what we have is a range of conversions which include fermentation, anaerobic digestion, and some other novel approaches which we're looking into in the future. And the main product there is methane, or biogas. And I'll talk a bit more about that metabolic pathway in particular. Then down here is those thermochemical conversions that I mentioned before, pyrolysis, gasification, and also catalysis to liquid biofuels, which all include those hydrocarbons and natural oil products that we get. Okay? So that's it. Important to understand from the outset that bioenergy includes a hell of a lot of feedstocks with a multitude of conversion technologies to produce quite an array of products. And the importance is that whenever we're testing the feasibility of a project is that we are not, we're basically technology agnostic. It's like we have a feedstock, but we want to be able to match the right technology so that we get the optimal conversion, right? So going on to the next part is end utilization, or what is the products. We already had a look at some products, but how do we utilize bioenergy and what's its importance in place of renewable energy? So as we mentioned before, bioenergy is that renewable which is very flexible and will have some really important components of, that will add into the renewable energy mix now and even more so into the future. So it's used across all of the energy sectors. So in that regard, its fit into the marketplace is very good. And what we mean is that it can be a form of a renewable energy form of bioelectricity. So for instance, when we're converting waste into biogas, the biogas can be run through gensets and that will be converted to electricity. So through combined heat and power, we can actually increase that efficiency so that we're also getting use of heat rather than just the electricity, because the actual conversion has a reduced efficiency. So if you run through biogas through a genset, you're probably only going to get about 35% conversion. At best, those gensets do about 42%. So you want to maximise the amount of use of that end product to the fuel. And so if you actually combine that power with heat, you'll get about 90%. And this is where we're saying that it's for heat. In countries in the Northern Hemisphere, where it's very cold as opposed to us, heat is a very good way of utilising bioenergy. Less so in Australia, but we will have, obviously, other ways to use it in terms of electricity. A bit more about how we can, what's best to use it in different countries. And more importantly, I think bioenergy will gain even more traction into the future as that source for liquid biofuels for transport. Okay? And I'll talk a little bit about that in terms of aviation in a little bit as well. There's another reason why bioenergy is important, is that it's dispatchable. Does anybody know what that would mean, dispatchable? Yep. Yeah, so you can use it at a specific time and start burning it, okay? So you can basically turn it on and off. When you've got renewables like solar or wind, they're only going to go while the sun is shining, while the wind is blowing. Whereas with bioenergy, so long as you've got the process running, it's going to keep going, right? It also provides baseload energy. What do we mean by baseload? Yep. Absolutely, it's the minimum amount. You guys know all this stuff. So, for example, our coal-fired power stations, they provide baseload energy. So in much the same way, bioenergy, give them a pat on the back, it's going to provide that baseload power, right? And I think you guys have had a talk, or will have a talk on smart grids, right? So I mentioned that in my interview. I don't know a lot about it, but I know that biogas, for instance, is becoming more important in terms of its use in smart grids as well. right? I won't go and talk about that because it's outside my expertise, but you can see that flexibility in bioenergy is really important. Okay. So, I mentioned I was going to talk a bit about advanced biofuels. Not a lot, because I don't know a lot about it, but, you know, this question is posed all the time. So, are advanced biofuels for airplanes ready for takeoff, right? I think there's a number of things that are all coming into place so that they are, right? I think the last, you know, decade or so, we've seen a bit of a, you know, to have, I guess have a link, it's a bit of being a lumbering takeoff, like slow and heavy, like these big things. But what they've found through, again, matching feedstock with conversions to products, they're getting an understanding of what's socially acceptable, what's environmentally acceptable, and so on, right? So we've had some instances where, you know, the corn being utilised for ethanol, and then there's other things with, you know, the food debate. And so they kind of become roadblocks to say, well, what's that next advancement? But I think, you know, into the future, there will be indeed that point where they've got the right feedstock, the right technology, so that you're not going to get some hurdles in terms of what's, you know, socially responsible. So now going on to biogas and closed-loop systems. This is my area, right? I think I just want to just recap where we are. So this is anaerobic digestion. How many people know about anaerobic digestion? Few people, right? Quite a few. So that's the most efficient fermenter we have in the world. It's the rumen, right? So we have ruminants, which are animals with 4 stomachs. They're able to eat grass, cellulosic, lignocellulosic products because they have a consortium of bacteria, protozoa, and anaerobic fungi, which are able to convert those feedstocks into biomass and provide it energy. So in much the same way that we are trying to capture that, they're doing it naturally. This takes me back to what I used to do as a rumen microbiologist. So after I did my honours degree in microbial ecology here, I went on and did a PhD with CSIRO, Division of Animal Production at Prospect, which is now been defunct, turned into all different types of things. But what I was working on was trying to get these anaerobic fungi from these sheep, these what we call fistulated sheep, and harnessing the enzymes, the cellulosic enzymes from those anaerobic fungi for industrial purposes. So it's not really for the faint-hearted, but what we actually have here is or cannula goes straight into the rumen so that we can take out rumen fluid and then isolate the bacteria, protozoa, or anaerobic fungi from there. Now, in terms of what anaerobic is, it's an obligate anaerobe. So we're looking at, you know, the anaerobic environment of, you know, minus 200 millivolts or something. So very, very anaerobic conditions. So all of the culturing techniques that I was using had to be in a glove box. They had to be in reduced medium, highly reduced medium. So we also had, you know, things like cysteine in it to reduce it. But basically what I was doing way back in the early 90s was to remove or isolate these anaerobic fungi, which are highly cellulitic, and to try to co-culture them with an ethnologen, right? So an organism which can convert the glucose monomer to ethanol. So it was what my proposal was about, to have a co-culture of a cellulosic microorganism, i.e. the anaerobic fungi, with the ethnologen, so that the anaerobic fungi can break down waste straw into glucose. The ethnologen can then use the glucose to produce ethanol. Right? That's what I first proposed. Now, when I said, you know, this is really good for biofuels, I said, we don't need biofuels. We're in the 90s, we don't need that. Let's change your project. And I said, oh, I really like biofuels. Anyway, what we ended up doing is more along industrial application of just isolating those organisms for enzymes, and which is really important even in bioenergy because we need enzymatic hydrolysis to get the most out of some of those really woody biomass feedstocks anyway. Right? So I thought I was a bit ahead of my time. I was told by economists in Canberra, no, we don't need anything about biofuels, and we sort of come round full circle, and I'm still working in biofuels, which is kind of nice. So, a bit of memory lane. So now going along the process of anaerobic digestion, here we have our ruminants, the most efficient fermenter in the world, and at the back here is our anaerobic digestion unit, right? So whenever we're trying to optimize biogas, we're trying to basically emulate the systems that are going on inside these cows. Now, to delve in a little bit of biochemistry, now, from the show of hands, there are probably about a third of you who already know a bit about this, and some two-thirds who may see this as the first time. But what I'll try and do is, not make it too simple for you, but also just to try to extend your knowledge in this area. I mean, it's interesting. I'm just thinking about myself. I didn't do any biology in year 11 and 12. I did physics and chemistry. Didn't think I was ever going to be a microbiologist. But, I think it's really important that you have those fundamental sciences, under your belt. Because when the first time I did biology was when I stepped foot into Carr's Law building, my first lecture here. And, I thought, yeah, I can handle this. It's the basic chemistry that you need, basic physics that you need. Because you do enzyme kinetics and things like that. It's really important. But anyway, so the actual anaerobic digestion process is in 4 stages. The first one is a hydrolysis, followed by acidogenesis, and then acetogenesis, and then methanogenesis. So what we have here is a consortium of microbes which act together to produce an end product known as biogas, which is around about 60-70% methane with the remainder carbon dioxide, with trace gases like H2S, maybe some siloxanes. And then we utilise the biogas for energy in the form of methane. So we need to do some sort of upgrading process so as we remove the carbon dioxide, which is normally done through a scrubbing process, various ways depending on the purity of methane you need. And then we go on from there. Now, to plunge a bit more into some biochemistry, for those who want to know a bit more, we start out with our feedstock, right, or biomass. So we call this suspended organic matter, right? And that organic matter is made up of 3 major macromolecules, your fats, your proteins, and carbohydrates, or these polymers, right? So the stage 1 is the hydrolysis. So basically, say, with lignocellulose or cellulose, you've got repeating chains of beta-1, 4-glucose, and then you've got enzymes such as the consortium of cellulases, which break down the various hydrogen bonds, whether they're on just the single bonds or in the middle, depends on what you're looking at. With the proteins, of course, you're going to have the other proteinases that will break down the various macromolecule into the amino acids components. And with the lipids, the enzymes, lipases, will attach to the substrate of to the lipids to produce the fatty acids. The glycerol comes out around here. So that's our first stage. And in anaerobic digestion, when we're trying to optimize the production of biogas, we find that the rate-limiting step is hydrolysis. And so this is what I was talking about, enzymes being very important in actually supplementing the microbial action and speeding up the process, right? It's the whole catalyst thing. So enzymes are very expensive, and that's probably why they were wanting me to work on it in my PhD. But I think that we will always continue to have roadblocks so long as we're going to have to supplement something that's at a cost. So what we really should be relying on is the natural processes that are within a system, because nothing's better than what's formed in nature. Now, going on to the second stage, which we call fermentation or acidogenesis. So this is basically when you've got your monomers or your more longer chain oligomers of amino acids, sugars, and fatty acids, which undergo fermentation to produce the intermediates propionate, butyrate, and alcohols. So you've got your volatile fatty acids, which is a component that is produced in naturally in ruminants. They actually use that as a feedstock for their growth. But here we have the VFAs. Now I'll talk a bit about volatile fatty acids a bit later in terms of actually monitoring these processes, but it's pretty important because they act as a feedstock for the next step, which is acetogenesis. So it's the production of acetate. So we have acetate and also hydrogen and carbon dioxide being produced at this stage. The last stage, methanogenesis, is basically where you produce methane. Now it's really funny, I went to a conference earlier this year in Leipzig, just out of Berlin, and the guys there at Germany's Premier Bioenergy Research Institute there are saying now methagenesis is the rate limiting step. But these guys, most of them are engineers. I'm not saying anything about engineers and scientists, but I work with engineers. But I think they're kind of missing a point that, yes, the methane organisms are a little bit more fastidious, but really, if you're looking at what a rate limiting step is, it really is hydrolysis. So that's just an aside. So I talked about the methanogenesis. Now, it's actually occurred, it's brought about by two different types of organisms, which we call the acetoclastics, and then the hydrogenotrophic methanogens, right? And they all come about to produce methane and carbon dioxide, which I said was basically biogas, 60-70% methane with the remainder carbon dioxide. Now, in trying to emulate that perfect rumen, we need to monitor this as microbiologists, as engineers, chemical engineers, biochemical engineers, so that we are going to optimise this as best as possible, right? So with all these various steps, you've got, as I said, a consortium of microorganisms all acting in concert, right? But there are some imbalances that come about, just like when we, say, overeat and we're not getting the best thing, we might get a bit of a stomachache, right? In the same way, our digesters will do that the same. So what might happen is that if we overload our digesters with too much organic matter, you're going to bring about a fair bit of hydrolysis, but what also happens is a build-up of acids, right? So we have the acetogens, which are pretty fast-growing, right? We talk about generation time in microbiology. Generation time, anybody know what generation time is? Yeah, basically the time at which it takes a microorganism to double its number, right? So through binary fission, say E. coli is the fastest. I think it's something like 20 minutes, right? But you can have some of those really, really long ones that take a week. And those really, really long ones are like these methanogens, right? But the acetogens are a lot quicker at doubling their population. So if you get an overload of them, they're going to produce a hell of a lot of these intermediates, these what we call volatile fatty acids. So whilst that volatile fatty acids are really important feed for the methanogens, too much of it is not a good thing. So what we get is inhibition, right? So you may have heard of process of inhibition. I'm not sure in biology, but it's a really important thing that we need to monitor. So as soon as we start to see a rise in volatile fatty acids in our digesters, we know that it's going to fail if we don't get, if what we do is pull back the amount of feedstock going in, so then that decreases the amount of volatile fatty acids that are being produced by the There's probably time was a bit of a stretch after all that metabolic pathway stuff, hey? But I was getting up to the fun part about methanogens, hey? So to limit inhibition, as I said, we reduce the amount of feedstock coming in, and therefore we can get the volatile fatty acids eaten up. There are other ways that we can monitor. pH is one way, because as soon as you start to build up with VFAs, your pH is going to drop. And they're all, have to operate at an optimum range. So our pH is probably about a 6.5 to about 7.5 range. As soon as you start seeing it lower down, it's time to say, okay, something's going on. Another important aspect, which not a lot of the biogas operators really look at, is buffering capacity. Right? Buffering capacity is determined by the amount of alkalinity. And what we see there is a ratio between your alkalinity and your total acids. And that ratio is really important to look at as well, because if you get a drop in alkalinity, it's going to be a better indicator than your pH, because if your pH starts to drop, then it's probably too late to do anything about it. So it's really, as I said, important to do this process monitoring and control, mainly because we've got methanogens, which are the ones that at the final stage have about a week generation time, a lot more slow growing, a lot more fastidious or fussy compared to the acetogens, right? So very important. Now, in terms of how we've taken that natural environment of the rumen out to produce something in an industrial sense, it's quite simple, really. And the technology goes from very simple to very complex, depending on the amount of money you can spend, of course. Now, in your conventional single-stage anaerobic digestion, you've basically got all of those 4 stages in the one tank. So to start, we have a preparation buffer tank, where you have the receival of feedstock. It's then mixed with amount of water, depending on how much total solids you need. So we're operating at around about 3% total solids. You can get the dry AD work as well, which operates 15% and up. And again, it depends on your feedstock. Once you've got this receival tank and you're happy with the mix, as I said, it's got to be the right mix for the organisms. We put it into a digester, which is normally heated mesophilic. Mesophilic is a term which says that, it operates between 15 and, say, 40. But our bugs for anaerobic digestion love 38. It's like the body, So they'll heat it at around about 38, and we'll also stir it so as to bring about homogeneity. Once they've got the biogas coming off, it will then go into storage post-tank treatment as well. And then that can be recirculated, depending on how much of your volatile solids is left or your organic strength. Now, in certain cases, we can actually split the process to what we call a 2-stage anaerobic digestion. So this kind of goes back to the metabolic pathway, which I showed, which said, okay, we've got acetogens and we've got methanogens. So this is taking the advantage of those 2 different types of organisms and trying to make each of them happy so that we can control that. Okay, so here we've got the preparation tank, we've got hydrolysis, acidogenic stage, and then once we've got the volatile fatty acids at an appropriate level, we can then feed that into the methanogenic stage digester, where the biogas is then produced and stored. That, of course, is a little bit more expensive, and in some cases it's just not appropriate. So I was talking about the different levels of technology. The large majority of biogas production actually comes from the developing nations like in Nepal, India, and even in China, where they're actually using very simple containers which use the scraps from their kitchens and, say, from the cattle. They put it into these digesters, get the biogas, don't even really remove the carbon dioxide, and they're using it for domestic purposes like cooking and like. Now, the impact that has, this sort of system, so small systems on the developing nations, is huge in terms of its positive impact. So I did a conference down in Canberra last year at the Crawford Fund, which is around food security. And we talked about the impact that these sort of simple things have on developing nations. So we can think about, say, in Africa, where you have women who spend hours and hours just simply gathering firewood for fuel, right? It could take 4 hours. What they're doing now is educating them to produce biogas using the cattle slurry that they have on their farms or their kitchen waste. And so then they can use the biogas for their domestic cooking and also their lighting. So what the impact it has is reduces the amount of time that these women have to do in collecting firewood. It also means that the methane that they're using is a lot cleaner than the kerosene that they might use, and also the firewood itself produces particulate matter, which has then health issues. It also frees up the time for them so that they can educate their kids, because they're not out collecting firewood. And also the lighting quality of the biogas run lights are a lot better, so the kids can actually study for 2 hours longer. So you can see that a simple thing like that can have some great impacts. So we're talking about, some social things and environmental. Now, to continue on the closed-loop systems, I want to just highlight an example there of food waste. For those of you in Australia, we had the War on Waste series, right, with Craig Rucastle a few months ago now. And it's starting to highlight a few issues. The out-of-spec bananas, how much are actually being wasted. The corporate responsibility and sustainability that some of those leading supermarkets have to have, right? Now, food waste is an example of a feedstock which fits perfectly into what we call a circular economy. How many people have heard of the term circular economy? Few. Right, I'm hoping that's going to be a big thing into the future, because it's got the potential to underpin a lot of the way that countries can be competitive into the future. Anyway, food waste. We can produce biogas. You've learnt all about that now, to produce heat and electricity and also fuel, those 3 market sectors. And that is good for small businesses, organisations and community groups. I just mentioned some of the importance in the developing countries. At the same time, which I haven't mentioned yet, biogas's byproduct, remember the tanks? Once you have utilised the feedstock, you're going to get a little bit left over. And this is what we call sludge, or digestate. Now, that digestate is a great fertiliser and soil conditioner, because basically it's undergone a pre-treatment, which in fact is readily available for the soil microorganisms. So what that's doing is replacing synthetic fertilisers, which are on the rise in terms of cost, and also not really good to produce in terms of fossil fuels, right? So we've got a two-way win here. So that then brings about the ability to grow food, and then that circle is complete. Which, by the way, I forgot to mention, with these developing nations, they do use the digestate to put on their crops. And what they're finding is that they can actually increase their growing period throughout the year. So they're actually going to get an income into their farming activity, which they didn't have before. Now, just some examples of food waste around what I'm seeing internationally. The UK are starting to become quite the leaders in food waste. So all you guys from the UK, hands up. I'm quite pleased with it. Do you guys know much about it? And I know you do, Annie, because we were talking about it last week with York Uni. Yeah. So York University, they're showing good leadership. They're collecting their waste, food waste from refectories, and providing it to our biogas operators so they can stuff it into their digesters and make energy and fertiliser. But what UK is doing well is also the utilisation of digestate and putting it back onto the land to complete the loop. For all those American guys out there, you guys are doing a good job too. Disneyland, they're doing corporate responsibility. A couple of years ago, they put in an anaerobic digester. They're collecting food waste on some of their theme parks there. And I just read about New York City. They are getting their collection system so that the Big Apple, that Big Apple there too, is collecting their food waste. Now, can you imagine that? New York City is huge, isn't it? I'd love to go there. That is going to be a huge, huge logistical operation, but they're doing it, right? So there's things happening there. In Australia, we have 3 anaerobic digestion facilities which take food waste. One's in WA at Jandakot, Rich Grow Food. That's actually a really good example of a closed-loop system, because Rich Grow, if you guys know, they're a composting company, and they're making use of food waste that's coming in along with some other waste, digesting it to produce electricity for their own site use, and any excess is being put into the grid at a very low FIT, mind you, but that's Australia. And they're then going to bag the digestate for compost, because that's what they do. But the next step they're going to do is any of the carbon dioxide which is being removed from the biogas is actually being fed into their greenhouses so that then they can produce more food for plants. So a really nice thing there. Another place in Sydney here, just out at Parramatta, not far from where I grew up, is Earth Technologies plant at Camellia. Right? So that had a pretty shaky start because anaerobic digestion is pretty hard to do here in Australia because we have minimal financial support, but I'll talk a bit more about that later. But they're getting all of the fruit and vegetables that sit from Sydney Market, bringing it out to Parramatta, and then converting it to electricity, and also bagging that for compost. And we started one down at Yarra Valley Water, down in Melbourne, which has only been commissioned a couple of months ago. So some early days for Australia. We tend to go more along the utilisation of waste because it's seen more as a liability. I'll talk a bit more about that within my project work, which I will do now. So my area is concerned mainly with Australian red meat processing, right? It is Australia's second biggest food manufacturer. Accounts for a lot of GDP. In Queensland, this is my backyard now. I grew up in Sydney and I did a tree change, went up to Toowoomba, which I love, and this is the Darling Downs, a very fertile part of the Queensland. It basically came from volcanic origins, and we've got a whole amount of basalt soils, which is very fertile and produces a lot of cropping. Anyway, so this is Oaky Beef Exports, which is Australia's third largest red meat processor. Queensland itself actually slaughters about 50% of the Australian herd. So if we're right in the thick of it in the southeast Queensland area. But what this industry is very resource intensive, very energy intensive. So it needs a lot of energy, it needs a lot of water. And to compete globally with the likes of Brazil in terms of slaughtering cattle, they need to lift their game in terms of being competitive. So just to outline sort of some of the processes here, obviously it's owned by Nippon Ham ONH Foods, which is a Japanese company, and they export a lot of packaged meat to Japan. So they have, along with their kill floor, doesn't sound too good, but they have a packaging and boning unit there as well. But with that comes a lot of use of water, a lot of use of heat, right, because they need to disinfect everything. Therefore, they need to start to look at how they can be more economic. How can they displace their fossil fuel use? They have a high need for natural gas in their boilers. So they started thinking, well, gosh, we produce a hell of a lot of wastewater. We need to treat it, right? And the Australian red meat processing does it in a way of anaerobic ponds. It's the easiest way. So just to go through this in the aerial photography, this is the plant, this is the kill floor, this is the cattle yards, and what happens is that the wastewater goes into this first primary lagoon here. It's basically an anaerobic digester, but in Australia it just looks like a big dam. It's pretty simple. And what happens over time is that it forms this crust, mainly from the high load of fats, oils and greases that comes from slaughtering cattle, as you imagine. So that creates the anaerobic conditions, right? But what happens is that we get this methane going up into the air. So you might remember that a couple of years ago there was a thing called a carbon tax, which has been abolished since. Some of those red meat processors were staring down the barrel of a lot of money to pay because they were the biggest emitters of greenhouse gas emissions. So what that did was force them to look at how they have to change their practice. So they started covering their ponds with high-density polyethylene, HDPE covers. And then they just simply flared it. Oh, gosh. They'd go and convert methane, which is 25 times more potent than carbon dioxide, and then the carbon dioxide went up in the air anyway. But things have evolved since then. But just to go through the process, after the anaerobic pond, it goes into a a polishing pond, and this is what we call a serpentine, so that by the end of the aerobic polishing, it is at a quality which can actually be irrigated out on the fields. So it goes into this big storage pond, then goes out to a centre pivot as irrigation, and then just fertigated onto their crops. Those crops are then used to feed cattle. So they kind of have a good closed system, but it could be better, and it needed to be better in terms of environmental concerns and economic. So they did some sums, they came up with a business model, and they thought, we're going to be leaders here and put in a waste-to-energy facility. So down on the field, from the aerial photograph, this is what these things look like. Apart from being very odorous, they are emitting methane into the air like you would not believe, right? And there's still lots of them out there that aren't covered. So it's an issue for them, and it became a huge issue, especially when there was that carbon tax that was going to be introduced. But then they said, look, we can actually use that methane on site. They looked at the amount of natural gas that they use in their boilers. They looked at the projection of the cost of natural gas into the future. And they said, well, if we put in a anaerobic lagoon, which is covered, capture that methane, feed it back into the boilers, we think we've got a pretty good way of paying this back in, say, about 5 years. And that's what businesses tend to look at in Australia because of the minimal financial support we receive. But it's pretty ambitious. Ambitious from the point of view because I work with these guys in terms of optimising this. So what they've got is what we call advanced coral technology, or a covered high-rate anaerobic lagoon. So we talk about high rate is the amount of time that water spends in these lagoons, right? Normally, for these ones, it's about 20 days, and that's pretty long. And it's about, remember that metabolic pathway, it's like how long it takes for the microbes to basically degrade the organic matter so that there's nothing left. But what we're doing here is trying to speed up the process, and we're doing that kind of in a two-stage way. So you remember that diagram I said? So here is the equalisation pond. That is there primarily to sort of standardise the substrate. So we're not having these huge fluctuations coming in. Because on a red meat processing plant, you've got different numbers of cattle coming in over the seasons. You've got different waste streams. Sometimes pumps break down. Try and work with site engineers, my goodness. You know, you've got these different streams of red stream, green stream. And it makes for a very variable feedstock. We want to know exactly what's coming in there because then we know exactly how to operate that thing. Anyway, the equalisation pond is there to, as it says, equal things out a bit, buffer, sort of. It stays there for a couple of days. Okay, so that's kind of stage one. We've measured VFAs, pH, COD, which is your chemical oxygen demand, which is like indicative of organic matter content. And then it flows through this main digester. So unlike that nice little dome one that you saw previously, which is much like the engineered ones that you see in Europe, we just have these lagoons for the most part treating livestock waste. But it sits in there for, it's supposed to be 7 days, but we don't have the right optimal conditions, so it's sort of sitting there at 18 now. But anyway, as it's producing the biogas, it's then stored here over the weekend, because normally the shifts are 5 days, then the weekend, and then 5 days on again. So what we want to be able to say is that over the weekend we've got enough biogas so that there's enough to then turn on the switch so that the methane is then diverted back to the boilers and then displaced. Currently we're operating about 60% in terms of the amount of natural gas they wanted to displace. They did do the calculations, it was about 45% they want to supplement, which is quite a large amount. We're getting there, and I think in a year or so we'll be able to get there to the maximum amount. But with that optimisation comes some really important lab studies that we need to do. Right? So working at a field level is really hard. You know, as I said, with particularly in this area, I guess with any area, you've got a multidisciplinary team of scientists, engineers of all types, whether they're chemical, electronics, mechatronics, biochemical, and also economists at the end, because if this doesn't actually make money, then it's not going to be any good. But the key to this is this thing here, which a lot of engineers think it's a black box. I'm afraid it's not. There's living organisms there that you need to keep happy. So this is where the process monitoring and control comes in, right? So on this side, we've got all of the various important parameters, like temperature. We know that if you're operating at mesophilic, that you're going to be the best. And we actually see, because this isn't unheated, it's not stirred, we get a nice drop in biogas production over winter time. I've been seeing the sheets just last week. We had some cold nights in Oakey. Darling Downs is not as a good temperature as you might expect the Sunshine State. We're actually on the Great Divide, so we get some pretty chilly temperatures, -8 sometimes. So that actually impacts on the temperature of these lagoons. And so with that, you're going to get a drop in biogas production. But what we can do is minimise or regulate the flow of feedstock so that you're not going to get a build-up of volatile fatty acids, because this is, again, another one that we're looking at. The alkalinity one's another important one. So in the lab, we have special equipment which, first of all, tests what we call biomethane potential testing. So in this automated gear, we've got the sludge, which acts as like the inoculum, and then we have the wastewater from the actual abattoir, and then we can actually automate that process, heating at 38, stirred, and determine how much methane is actually produced. That's a closed batch, which means that it runs for like maximum of 30 days, but we don't have a constant input of feed. We have other digesters at 10 litres, at 30 litres, which then simulate these conditions a lot better. So we're helping optimise this system, saying this is what's happening in the lab, and talking and working closely with the plant engineers to make it happen. So there's just some of us out there collecting wastewater samples. This is a thing called a save-all, which is where all the wastewater comes. It's not for the faint-hearted. If anybody's been on a rendering facility, it's a bit smelly, but you get used to it. And it's interesting how you can bring all that smell back to a lab as well. But then again, I've always been part of that, I guess, right from my PhD days when I was collecting rumen fluid and fecal samples from animals like elephants and giraffes and things like that. So there's a bit of a common theme there, I think. My aim is to make shit sexy. So, coming down to the last section, what's about the sustainability of bioenergy and what is its prospects into the future? So, just a bit of a blurb here about some things that IRENA have put forward. IRENA is the International Renewable Energy Agency. So that's that big entity that sits across the globe and supplies a lot of information to the International Energy Agency. One of my roles, apart from doing academic research, is a national role with the International Energy Agency representing Australia in Task 37, which is energy from biogas. So what that allows Australia to do is sit around a table with 14 other member countries who are doing biogas and exchange ideas about what's your best practices, what's the economics behind it, what sort of technologies are coming through. So we meet twice a year and we discuss all these things, and then we try and report back that to our country so that we can increase the adoption of biogas in Australia. So I've met some really lovely people over the course of the last 3 years. I'll be going to Denmark in September. We had our last meeting in, which one was it this time? In the Netherlands. Last year, at the end of last year, we actually had it in Toowoomba, so it was a bit of a coup for us. It was the first time that Australia had hosted a meeting. But we learned an incredible amount of information from this exchange. But at the same time, I've noticed that the overseas countries are also looking at Australia in terms of what they can learn from us as well. Because a lot of the growth of biogas, particularly in Germany, has been based on feed-in tariffs and subsidies. They've had major changes over the last 3 years, so that the growth of their 10,000 plus biogas facilities have relied on subsidies, particularly from their agricultural plants, which about 8,500 of them. But because there's less financial incentives, they say, well, Australia, how are you doing this? I said, well, we'll do it with difficulty, but it can be done. It has to be the things of the utilisation of waste. It has to make business sense in terms of how you're using it on site and the like. But if we look at bioenergy as a whole, with all its various technologies and all the various end products, we see that bioenergy is the most widely used renewable energy source worldwide. And, and that can be just from simple things like, burning biomass, or even the amount of those domestic biogas plants that are in China alone. That's what makes bioenergy the biggest. I'm not sure how many of you knew that that was the most widely used. Yeah, you? Right? And the biggest thing into the future is that IRENA estimates it could account for half of the renewable energy needed in 2030 to meet climate targets. So much of the drive in bioenergy these days is all around climate change, because it's one of those, obviously, renewables which will reduce greenhouse gas emissions. From the point of view of the fuel that it produces in terms of methane, the most environmentally friendly one, but also the fact if you're utilising waste, organic waste, which degrades naturally to produce methane, you're going to reduce greenhouse gases as well. So it comes more from a waste management perspective. And this is where Australia is getting into it as well. So we all have these needs to reduce greenhouse gas emissions, and this is where bioenergy is really going to play a big role. But the important thing here is what I've said, is that to gain the support of public expanded use of bioenergy must be socially, economically and environmentally sustainable. So the big three pillars need to be looked at. Now, there was, I just put this up here because that was one of the things that came out, over the last decade or so, when we had mountains of corn being, cultivated and then harvested for ethanol production. There was, it divided people to the point where there were stations saying, we actually have gasoline which doesn't have any ethanol in it, and some people would rather that because things. But it's really around about how we then engage the public so that they understand the complete picture. I just probably can't read this, but I will go through this. I put this up because I think it's a lovely little introduction to bioenergy, and it comes out of a group of the UK Supergen. I'm not sure any of you know these guys, but that's the link if you want to download it. It's a neat little comic book. So it's a graphic illustration they talk about of bioenergy. And it summarises what bioenergy looks like in an ideal system in order for it to be sustainable, affordable and secure. So I'll just read through it. So an ideal bioenergy system could be relied upon for as long as we need it, right far into the future. So this is just reiterating the importance of it into the future. But to do that, we need to think of the whole system, to look at it in a holistic way. So which energy sources are most appropriate? So how does it then be part of that baseload energy? How can it be dispatchable, right, with solar and wind? So such system would provide controllable energy to complement intermittent energy, such as sun and wind. It has to be cost effective, right, but the lowest cost way for us to decarbonise. So I want to talk a little bit about, what happens in Australia. I kept on saying we don't have much financial support in terms of feed-in tariffs. We got large-scale energy certificates, but that's basically it. So the business case is more around how do we displace fossil fuels and how do we get the best utilisation on site. And this is how we're seeing, especially that example of the abattoir, in that they're displacing their natural gas needs by supplementing with the biogas produced on site. So it's coming both from an environmental point of view, an economical point of view, and also they're looking at being socially responsible. Now, the other thing here, it would have to have a positive impact on wider sustainable development goals. Here, that would have to keep levels of carbon dioxide in the atmosphere in balance, right? So that was one of the things, I think even recently was a report out of the IEA on the Chatham report, which they look at life cycle analysis. So that's another thing on LCA. Is like, okay, from cradle to grave, you know, how much carbon are we actually reducing here? And here it would avoid harmful environmental and social effects elsewhere. And the production would have to keep up with consumption. So there are some of the factors that you need to consider when assessing the sustainability of renewable energy in the form of bioenergy. So bioenergy in Australia, it's a race, and we're that little, I reckon, there's that little red person who's trying to keep up. We do lag behind other developing countries and even developed countries. So even though we are a developed country, we are not really up there in the game, and that's for a number of reasons. We are a resource-rich country. We know that we have governments who would like to utilise coal. They see that as a competitive advantage. But less and less so is that reliance on coal, right? We've seen what's happening, particularly in the last couple of years. And that has had some impacts in terms of how we adopt renewable energy. From the point of a couple of years ago, we couldn't even decide on a renewable energy target. The RET hadn't even been set. And when they did set it, they reduced it. But it has a positive impacts in a market which is quite nascent or just emerging. People will not invest when they don't have confidence. And if they can't even set a renewable energy target, we actually saw that there was reduced investment into bioenergy projects. And this, as I said, you know, it has all these impacts. So in terms of bioenergy, it accounts for just 1.5%. That's 1.5% of total electricity generation. As about this year, we are around about 15% renewables, much of which is coming out of hydro, which I don't think is really going to be sustainable. But then it's following up with solar and wind, and then comes bioenergy. But if we compare ourselves to some of the major players in bioenergy, Finland, 24%, Sweden, 22%, and Denmark, 17%, right? But a lot of these, you know, Finland, they've just done a ban on landfill recently, right? Australia, we're a big country. We've got a lot of room to bury our rubbish, but things are changing. We've got levies increasing in South Australia, Victoria, New South Wales. There are some areas in Victoria which are banning landfill. Fortunately, Queensland, we don't have a levy. But you know what we're seeing is that waste is being trucked or railed as far away as Victoria and New South Wales and dumping it in Queensland. So things are going to have to start happening because it's costing that state millions to dispose of other people's rubbish. But we can use that resource to actually produce energy, right? So you can see the different drivers which will make countries go toward a particular thing. Now, I talked about the circular economy. Now, I think it was back in December the year before when the EU, the European Union, launched a very ambitious plan on circular economy. And they see this as a way to be competitive globally. And what that means is that they place legislation so that they can manage their waste and provide the right policies so that they can have increases in bioenergy production and the like. So you've got to have the right policies behind things. So I said there's two major things with bioenergy at the moment. The one is policies, and the other one's climate change. So they go hand in hand, really. So, which leads me to the last bit around communication. It's vital. It's the thing that's going to make people aware of what things are going on and how they can then, you know, vote and be more informed, right? So I just want to go through this example, and I'll show you a little YouTube clip to show how people are starting to communicate the message so that people can actually get an understanding. Here is a nice closed-loop system. It's coming out of Italy, the CIB people, and also with Michigan State University. But basically, they've got a system which, at the heart, is anaerobic digestion, which is going to collect feedstock from animal waste, like manure. Okay? It can probably bring in also other waste, depending on what they're doing. Things like energy crops. So in some farming land, which might be fallow, they think, okay, let's do a sequential cropping, because that can be actually seen as a value add on their farm, right? So instead of being as a commodity, which they'll have to sell off, and when they don't know what the prices will be, they'll go and grow something because they know that if we stuff it into that digester, they're going to get energy, right? So it's a different way of doing energy crops, which don't compete with food, right? So in goes the feedstock, out comes the electricity into the grid, if they've got a good enough feed-in tariff, and they will make use of that leftover sludge as digestate so that they can fertilise their crops. Nice closed-loop system. They can then utilise biomethane to the grid. Now, biomethane is a little bit different to methane. A lot of people just think biomethane is methane. We talk about biomethane as an upgraded product of biogas. That is, it needs to undergo some scrubbing to remove carbon dioxide and other impurities so that the methane is at a purity which will be acceptable into the grid. Okay, so that's nice. I'll just show this. Hopefully it will work.
There is a lot of talk about biogas. It's said that it pollutes and smells bad and that it damages the territory. Every time a new plant is proposed or planned, citizens set up no biogas committees. Nonetheless, are we really sure biogas is so damaging and detrimental? If, with the manure of a farm, instead of just amassing it for compost making, we use it to produce heat, it doesn't stink, it doesn't pollute, but it could warm schools and hospitals. We would all benefit from it. If, with the peel and scrapes of fruits and vegetables, instead of just binning them, we produce electricity for hundreds of families, we would all benefit from it. If, with damaged crops, instead of disposing it, we produce biomethane, we would avoid importing biofuels from tropical countries, decrease goods traffic towards big plants, and make our vehicles greener and cheaper. We would all benefit from it. If instead of leaving fallow land, we increment crop rotation, and with the second harvest we produce digestate, the land is more fertile, agricultural businesses are more efficient because they get rid of chemical fertilizers, and we improve the quality of the food we bring to our tables. And we all benefit from it. If the plant is well designed, proportioned to the agricultural business it's meant to, and managed adequately, it doesn't smell bad, and it doesn't impact on traffic deriving from long-distance transports or waste, and companies make the most of their byproducts. We all benefit from it. If we make out of biogas an excellence made in Italy that offers jobs to an increasing number of people, we all benefit from it. A biogas plant is not a monster that burns waste, but a great resource for the environment and the territory that enables agricultural businesses to be more efficient and competitive, reduce our chronic dependence on other countries' energy, as well as providing electricity, heat, digestate, the natural fertilizer, and biomethane, the eco-friendliest fuel on Earth. So, if biogas is done right, we all benefit from it.
So that is just one example of the way that we can communicate the likely benefits to inform public. So I chose that example because I guess internationally where biogas is a bit more advanced in Australia, what you're going to start to get is a little bit of kickback from the public, okay? So in Italy, they've gone and had to do these things, even though they're quite advanced. So that was just an example. So along the communication side of things, I just wanted to talk a bit about how I find communication is important. Right? As a researcher, first and foremost, a KPI I need to fulfill is publications in journals, right? Publish or perish. But equally important is that communication out into the wider public. In fact, I think that has far more impact than any research that's tied up in these scientific publications. Doesn't go beyond the scientific community, we're just simply, preaching to the converted, right? What we need to do is actually go out beyond there and to inform the public so that they are not misinformed, because it's amazing how misinformed they can be. So over the last few years, particularly how I've seen my role with the International Energy Agency and to try to get it out there in the public, also to work closely with industry as I do in my research centre, I go out and I produce pieces or opinion pieces into the conversation. How many people read the conversation? Yeah, good. It's a good source of, I don't expect many high school people, students do, because it's basically aimed at the general public, and it's a forum basically, or a platform for academics to go and put out their research into, with a bit of journalistic flair. So it's kind of got me out of my comfort zone. I can write proposals for projects to get external funding till the cows come home. I can write publications till the cows come home. But this is sort of different writing. It's sort of pitched at a 12-year-old level, and it's supposed to be informative. So I started putting out things like, this one here was out in 2014-15. Biogas smells like a solution to our energy and waste problems. Right? It was the first time that a publication had been out there on the conversation, so the editor snipped it up. The next one I wrote about was Bioenergy, making money and clean energy. And I started looking at sort of the news cycle and how it's really important to jump on topics at a really timely time. So I was watching the news, and I think the Clean Energy Finance Corporation, for those who know of the CEFC, last year, the year before, was it 2015? Yeah, they were mandated to say that they had to do projects which were not, or had to be seen as emerging. So they weren't getting to support any projects around solar or wind. And so the government was basically ordering the CFC to say, we want you to invest in these sorts of projects. But I said to my husband when we were watching TV, he said, they didn't even include bioenergy. Where does bioenergy fit? And he goes, well, probably because they don't even know what bioenergy is. It's dead right. So I put up a piece there saying, well, bioenergy is actually standing on its own 2 feet here. I talk to the guys at CFC all the time, and I said, give us an ROI on that. What are your projects, your return on investments? They said, they're not too bad. We will provide some finance to these projects, which they don't have to pay back, but we're finding that they're actually standing on their own 2 feet. I said, well, then why isn't the government saying that, right? So you've got to not only inform the public, but actually inform the pollies as well, which I'm sort of having to do a lot more of lately too. Then when I was down at the Canberra, at Parliament House, doing this thing on food security, I put out this whole thing of circular economy, because it's never even up here in the government. We wouldn't know what it is. So I said food waste, right? So what I started seeing around the states is that they're setting their own renewable energy targets in the absence of any other government, what the feds are doing. Couldn't even do, go on an RET all that time. But the states were actually taking things in their own hands. The regions were. And so I started to highlight some of those things there. And then I was contacted by the conversation while they had the war on waste thing going on. And they wanted to do a landfill story on what actually is in Australia, an explainer. And the good thing about gauging the public's knowledge is that they can actually go online after reading the article and write comments. And the surprising thing about that landfill one, they actually like landfill in Australia. I couldn't believe it. And when I started saying that, we can actually capture methane from landfills, one comment was saying, oh, I didn't actually see landfills as a resource. So yeah, we basically can capture the resources before it goes to landfill so that they can provide energy and the like. So communication is key, right? And I think that I recall actually Dr. Carl talking last week when I was here for the day about his experiences and how, he was watching something on TV when he started saying, this is crazy, this is ludicrous. And then he, went and went for, stepped his foot into some political arena and ran and said to you guys, you all might be interested in science, but I could see he was urging you guys, think about a career in politics. Now, you could think about that, but the other thing is that you can maintain your interest in science, but you can influence the politicians too, right? So that's the other way. And, you know, I get invitations to be expert witness in inquiries around waste to energy in some projects in Australia. So it's actually having some impact and being able to influence those decisions. So with that, I just wanted to end on a note to say that's not all doom and gloom in terms of like our transition. So some fuel for thought. There was an article that came out on GRIST yesterday, and GRIST is a really fun magazine, online thing out of the US. And they said that 100 fossil fuel companies create 71% of our global emissions. It's amazing, I thought. And it's all the ones that we know, like Shell, ExxonMobil, Chevron, right? But it's going to be up to them too. They're going to get more pressure to do something. So it's not just outside the fossil fuel companies that are doing stuff. It's actually going to come from them as well. So from that article I read, that Shell is actually looking at this as an opportunity, and they're going to have to do something in terms of changing the way that they're doing things so that they're doing things in the renewable area. So on that note, I just wanted to leave you with this. Some of you may have seen that or not, I'm not sure. But I think there is hope, even though it is an age-old argument. Thank you.